Okay, so continuing on in chapter 7, we're going to talk about scale diagrams and reductions this time. So in 7.1, we talked about enlargements, and that's what it sounds like. The picture was bigger than the object. In 7.2, reductions, that's the opposite. So what happens is that the scale diagram is going to be smaller than the original object. And so stuff like a good example of that would be blueprints. You're never going to be able to draw a picture as big as the building, nor would you want to. So that would be reductions as an example of blueprints are an example of reductions. So same learning outcome to draw and interpret scale diagrams of two-dimensional shapes. Okay. So it says that a scale diagram can be smaller than the original diagram. This type of scale diagram is called a reduction, and a reduction has a scale factor that is less than 1. That's important that you make a note of that somewhere in your learning journal. So when you're reducing, it's smaller than 1. When you are enlarging, enlarging, your scale factor will be bigger than 1. Okay, so that's important that you make note that it will be smaller than 1, okay? All right, so example number 1 is nice and easy. It says find the scale factor for this reduction. And remember that your scale factor can always be calculated. I'm just going to go SF for scale factor. Can be calculated by taking the size of the diagram and dividing by the size of the original. All right, so we've got this picture here, and it's a circle. And you got to think, all right, what would be the easiest part to measure in this circle? Like, you can't measure, you can calculate, but you can't measure the distance around. Okay, that would be too hard. But it's not too difficult to measure the radius, or the radii of both, okay? So, if we counted squares, the scale diagram is 2, and the original is 5. Right? 1, 2, 3, 4, 5. So the scale factor will be the diagram over the original. So 2 divided by 5. Which would be 0.4. Okay? So the scale diagram, this is what we drew. This is the actual, is 40%, because 0.4, 40% less than the original picture, okay? It's a reduction, so it's less than 1. All right, so let's move on and pause, try to check yourself, and then come back. All right, so check number 1 says find the scale factor for each reduction. And they've got just a length line here, and this is the original, and this is the scale diagram. So they ask you to measure the length of the original. So I got out a ruler. I got 3.1. You might get somewhere around there, as long as we're in the same ballpark, okay? And then it says measure the line of the line segment in the scale diagram. I got 1.5. So it's reminding you here that the scale factor can be calculated taking the length on the scale divided by the length on the original. Okay, here's the scale. It's 1.5. The original is 3.1. When I take 1.5 and divide by 3.1, I get about 0.48 or closer to half. Okay, so I'm just going to round that up to say the scale factor is half, 0.5. Okay, so this is about, my scale diagram is about half of the original, which looks about right. And then B says length, we've got a rectangle here. And so when you're trying to find the scale factor of something like a rectangle, you only have to do one side. You don't have to do all of them, just one side. And so that's what they're saying. They said use this length here and then use this length here. So length of original. Here's original. 1, 2, 3, 4, 5, 6, 7, 12. The original is 12. The length of the rectangle on the scale is 3. Scale over original. Scale over original. 3 divided by 12 is the same as 1 over 4, 4.25. So this is a quarter, or 25%. of what that is, which again seems reasonable. All right, example number 2 says the top view of a rectangular patio table has length of 165 centimeters and width of 105. A reduction is to be drawn with a scale factor of 1/5. Find the dimensions of the reduction. So, oops, no, there we go. So let's go ahead and draw a rectangle. That seems reasonable for a table. And let's label them. So because 165 by 105, I'll stick the 165 on the longer part, and I'll stick 105 on the other part. Okay, remember those are centimeters. So remember in 7.1, how did we get our new dimensions when we knew the scale factor? You multiply. You're actually saying it's 1/5 of the size, and of in math means multiply. So we're going to take both measurements and multiply by 1/5. Okay, you might be thinking, all right, I'm not sure how to multiply by 1/5, but you can convert 1/5 on your calculator to 0.2. 1 divided by 5 is 0.2. So on your calculator, you're just going to do 165. You're going to multiply by 0.2. Hopefully you get 33. Again, 105 times 1/5, 4.2 works out to 21. So the diagram will be 33 by 21. Okay? Easy peasy. All right, pause, do the check, and come back. All right, so the check says a window has dimensions of 104 by 89. A reduction is to be drawn with a scale factor of 1/20. Find the dimensions of the reduction. So right off the bat, they get you to convert 1/20, which is 0.05. The length of the original, it's, well, they said the length's usually the longer part, so we'll call that 104, and the width would be 89. It would not matter if you switch them around, but the length sounds longer than width, so we'll do the bigger measurement. So to find the length of the reduction, we take 104, we multiply by 0.05. So when you take 104 and you multiply by 0.05, you get 5.2. That's a really small number compared to what it was. It was 104 and now it's 5.2, but man, we really reduced it by a lot, so that's okay. All right, the width of the reduction, it's 89 times 0.05, which works out to 4.45. So the reduction has dimensions of 5.2 by 4.45. Okay, number 2. It says the top view of a rectangular swimming pool has dimensions 10 by 5. The reduction is to be drawn with a scale factor of 1/50. Find the dimensions. All right, starting with the scale factor, write it as a decimal. You need to convert 1/50. On your calculator, do 1 divided by 50, should get 0.02. The length of the pool, we'll take the longer one. So 10 times 0.02. The 10 means I move my decimal over one place. So I get 0.2 of a meter. Oh, it says convert it to centimeters. If I know 1 meter is 100 centimeters, then I can take 0.2, multiply by 100, move my decimal over twice to get 20 centimeters. Width of the pool is 5 meters. Width of reduction was going to be 5 times 0.02. Which is 0.1 of a meter. Makes sense because 5 is half of 10, so it makes sense that that's half of 0.2. Convert to centimeters, so 0.1 times 100. Every time you have a 0, you're going to move it over, so you get 10, which again is going to be half of that. So the reduction has dimensions of 20 centimeters by 10 centimeters. Now, why do you think they've gone from meters to centimeters? How come they're changing units? Can you think of a good reason why they're doing that? Well, think about a swimming pool. Would you really measure a swimming pool in centimeters? Of course not. You would measure it in meters because it's going to need a big unit. Would you measure the dimensions of a diagram in meters? Not at all, because it would be 0.2 times 0.1, which isn't that helpful, okay? So you got to think about that. Think about what makes sense in terms of units, because it's not hard to convert them. And if it makes more sense that a picture has to have smaller units and the actual has to have bigger units, then go ahead and convert them. That's fine. All right, that's section 7.2.